before even renting a place. We are Asian Intelligent Team, and we're developing BeFinder, an AI-powered platform that analyzes your business location profitability. Hi, my name is Rikal Shaputra. I'm a software and equation developer of this system.
Hi, my name is Jason. I'm also responsible for helping software and equation development.
Hi, I'm Kenny, and I'm responsible for helping software development and system architecture.
Okay, without further ado, let's go into the demo. First, you have to go to the identity. Next, to make sure that the user can pass the improvement for the ICP. Here, the user can have the platform, the dashboard, super simple. So the user have to do like place the pinpoint. Just imagine that the user want to open a business in specific location. This example is this place. And then the user just need to input the value, the width of the store. Just imagine the width of the store is 3.8 meters. And the daily operational is 12 hour. With the average of product price is like 20K in IDR. After that, the user no need to do anything except click the analysis. Every calculation is calculated instantly with our agent's AI. Here's the analysis progress. Show the progress step by step. After the analysis done, we can get the data. Here's the profitability analysis. From the data, we can get that the customer daily is 180, which the daily revenue is 3.5 million per day. And the profit instantly, the equation that we implement on this platform.
So this is our compact equation, which is used for finding the revenue per month. And there are a lot of symbols, and each symbols has their own meaning and purpose. And we also have conversion formula, like from pixel to meter. And there is also a value, value of an area equation.
Okay, thank you, Jason. And we can go into the overview of the flowchart itself.
So this is the flow chart. This flow chart shows how our system works from start to finish.
To make detailed explanation, let's go into this simulation. So first, from the first place, the user have to locate the pinpoint locations. After that, the system zoom and crop based on specified radius. With this tile floor layer imagery, the system shows the street version imagery, which means they do these three things. First, system categorize, filter, and predict the colors distributions. And here we gather three things: the residence, open space, and road distributions. In this case, we gather the place of 73% for the residence, 5% for open space, and 20% for road distributions. After that, the system calculates the meter per pixel constant with the error rate 30.5%. All of this is gathered to calculate the CGLP, which is current gross local populations. This conversion is used to know the exact area in meter square that convert also in a square kilometer. With this, we can have the CGLP constant from 16,000 multiplied by 0.056. The 0.056 is gathered from this. This is the conversion, the area of the screenshots, multiplied by the Jakarta density. So the system is going to know this exact location and gather the data from the census, which is 16,000 people in square kilometer in Jakarta, especially. From the calculation, we can get the data of 896 population for the gross local population. After that, we specify the calculation more detail using our color distribution of the population from the residential area. Here's the population is CGLP multiplied by resident distributions, which means the POPs is 896 multiplied by 73%, which is the distribution of the residence area. Here we can get the 654 population. We also calculate the road area distribution from the for the SQQM distribution. So the road distribution multiplied by the local area, which means 20% multiplied by 56,491. The 20% is gathered from the road distribution color from the previous data. Here we can get the data is 11,298.27 meters square. With this, we can get more detailed data, which is we can have the PDR, which is people density on the roads, which is POPs divided by the road area, which is 654 divided by 11,298. And we can get the 0.0579 people per SQM. From this, it means from our calculation, from our model, and from the specific location, we can know that in 1 meter square area, there is 0.05 humans, which means 1 by 20. After that, we calculate the average population capitalization per unit area of road, which is APC per unit area of road per unit of time. APC is width of building meters multiplied by average width of roads in meters multiplied by PDR, people per SQM. APC equal 3.8 multiplied by 30 multiplied by 0.05 equals 6.6 people. 3.8 is the width of the building. Just imagine that you open a store, which is your ice cream store, with have the width of 3.8 meters. Multiply by 30. 30 is the average width of the road in Jakarta or specific city locations. And also multiply by 0.05, which is it is a PDR data, which is people per SQM. Here we can get the data of 6.6 people. What does it mean? It means that in front of the building, let's say it's a Mixu with the width building of 3.8 meters, there are 6.6 people here per 1 unit time. And let's say the unit time is seconds. And 30 meters is the minimum road width in Jakarta. After that, we calculate the average population traffic per unit business time daily, which means APT equals to daily business time in seconds multiplied by APC. APT equals to 43,200 seconds, which is half a day, multiplied by 6.6, equals to 285,120 people daily. It means daily, the traffic in front of the store is 285,120 people. But we have to calculate the visitor capitalization of daily traffic because not all of the traffic intended go to the store. Let's say not everyone in the roads intended go to the Mixu. So the VCDT equal to visitor rate in percentage multiplied by APT. Here we can put the data of 0.1% of people intended go to the Mixu multiplied by 285,120 equals to 285.12 people daily. It means the people that visit the Mixu is 285 people daily. After that, we calculate the total people purchased daily because not everyone that visits the place is intended to buy things. So that's why we calculate using the purchase change rate from the TPPD. TPPD equals the purchase change rate in percentage multiplied by VCDT. So the TPPD equals to 90% as our assumption multiplied by 285.12 equals to 256.6 people involved in daily purchase. So that's why we can gather the data of the prediction of the people that involved in daily purchase in specific locations. But this is not enough. We're developing more robust equation to make it more specific. Here, we try to analyze this. The nearby point can increase error rate by area capitalization plus assumptions. The solution we developed the anti-error indicator equilibrium radius 20 to 30 meter in pinpoint user area. So here is the equilibrium point. So not everyone that have the near location intersects in the radius are having this are having like the same result. I mean, we implement like the ceteris paribus. Also, we develop more robust equation to predict the probability distributions. The problem is the traffic dynamic can result various of error on calculations. As example, different placement result different traffic. But current equations ignore the dynamics and just based on color distribution of sections area. So the solution that we developed is probabilistic distribution based on road type, number of road, and the junction. And we try to implement the basic junction probability distribution based on the area. But not only that, we also develop the Markov chains formula to predict the next 16 days probability for the profitability of the company or the store based on the weather. So here we call it weather prediction system with VCDT integration. We use a Markov chains to analyze the matrices and to analyze the next revenue for the next 16 days of the weather predictions. So that's it, our presentation, our demo, and our explanation about our equation that we implement. We build it from scratch and we develop it from scratch. And that's it from our presentation. Have a nice day.